All right, I assume you wanted more, Daniel, than just that. You want me to start adjusting it to see what changes? Or are you good with this?
And then a dielectric is always going to be negative.
The electric field?
Yeah.
It's always going to be opposite the direction of the electric field.
Okay.
So whether it's positive or negative depends on which way you define positive or negative. Which way is the electric field going to go in between the two plates right now?
To the right.
Positive to negative. And I will point out, notice that there is a formula for the total electric field, or the electric field because of the plates, that I did not write down because it's incorrect to use. The KQ over R squared. When should you use KQ over R squared to find the electric field?
And that's a point charge.
Yes. And this is definitely not a point charge. All right. Did you want me to adjust it, or are you good with this as is?
That's good. I just like when I get to a problem, going from word form into what do I actually need to solve for the problem.
Okay.
Is what I've been having issues, but getting the steps down is helpful.
All right. Any other questions on this, Jim?
Could I adjust it? Could
Oh,
you
okay.
do the same, like keep the same numbers and then add a dielectric into it? So like the initial and final values?
You want me to just put in dielectric and change something else, or?
Correct.
Okay. All right, so let's stick a dielectric in here. I assume that anyone writing this down has it down. So we will stick, of course, a blue dielectric. With a kappa of, let's make it 3. It is still hooked to the battery. So what's going to stay the same? Okay. And hopefully this can show up here. Let's see. So voltage is still 12 volts. That has not changed one bit. There's something else that's going to stay the same also.
Total electric field.
Yes. Looking at the second equation over here, my voltage stays the same, the distance between the plates stays the same, so my total electric field stays the same. But recognize that the whole point of putting a dielectric in there, it actually serves twofold purposes. One, it increases the capacitance, and two, it allows me to get the plates closer to each other without touching. So it acts as a buffer as well as it enhances. So whatever we come up with, just conceptually, I know that my capacitance should increase. And if I think about this first equation I've written over here, my voltage stays the same and my capacitance increases, so what else has to change?
The electric field of the plate,
Yes, because,
our sigma will end up changing as well.
our what?
Our
Oh,
sigma, the
Oh.
O.
okay, the surface charge density.
Yes.
And why does that increase?
Because we're increasing the charge.
Yeah. So we increase the charge on the plates, which has these other implications. I would have gone the other order, but we got there. So this comes down to, what do you want to do first? We could, I guess we can't use that first equation until we know what the capacitance is. So how's the capacitance going to change? Which of these numbers will change on the capacitance formula here?
Just the K.
Yep. Not a K. Kappa. It looks a whole lot like a K when I write it, but it is a kappa. So this one here becomes a 3. So you could just start from scratch and type it all in again, or just multiply this by 3. 6.51.
Yep.
Times 10 to the negative 9 farads. All right, so I've tripled my capacitance by putting this dielectric in. So that, I tripled my capacitance, so my charge has to triple also. Because, again, my voltage stays the same. Seven, 8. So about 7.8 times 10 to the negative 8 coulombs. Well, if my charge tripled, my surface charge density triples, because I'm not changing the size of the plates. So that is 15.9 times 10 to the negative 8. Now my surface charge density tripled, therefore the electric field from the plates tripled. Using the 6,000 number, because that math I can do in my head more easily. And done. And we can test our answers here is delta V divided by D, look at that same equation again, is delta V divided by D still equal to my total electric field? Well, yeah, except for rounding. And there's another equation we didn't use. Nope. The magnitude of my electric field coming from the dielectric itself, it's got to be the difference between my total and from the plates. So it should be about 12,000 newtons per coulomb. And if I weren't asking for magnitude, but by the absolute value signs I'm indicating magnitude, then the electric field from the plates, not the magnitude, but the vector itself and this vector would be opposite signs. One other check here. Because what the heck? Math is fun. All right. I know that my total electric field is sigma over epsilon, which is sigma over kappa epsilon sub naught. So my sigma tripled. So it's 3 times whatever my initial one was. Kappa is 3 and epsilon sub naught is epsilon sub naught. That's what I had the first time. The 3's cancel out, so my total electric field should not have changed. Or you can just plug in the numbers and see that it works. Questions?
When we insert a dielectric and nothing else changes, will it always be that clean of a conversion? It's not the right word.
In physics 152, yes. Obviously, reality gets a little bit more complicated because you're not dealing with an infinite plate. But
What would that look like, or is it too complicated to get over real quick?
I have to track it down. The formula for the electric field inside the plates, if I took 2 plates not assuming that they're infinitely large. Then the electric field in the middle will go straight across, and then you'll see some slight curving here. Probably curving it more than it should, closer to the middle, but. So the electric field starts to warp, so at this point right here, the electric field's pointing in that direction, here, the electric field's pointing in that direction. And so, so the formula depends upon where it is relative to the plates, how far it is down this way and how far it is that way. So it's a more complex formula.
Okay.
And with calculus and, 2 hours to kill, you can write.
So if you disconnected the battery, would the only thing in the problem that changes is the voltage, and then you just plug it in like we did for the changing kappa?
Your wording was off. You said the only thing that would change is the voltage. Voltage would change if all I did, back up for a second. If I had a capacitor here and I just disconnected the battery, nothing changes.
Okay.
Once I adjust something else, then suddenly everything starts changing. But just disconnecting the battery in and of itself does not change anything, but it does fix the charge. So if I disconnect the battery and then stick the dielectric in that order, then this would stay the same as before, and you'd stick in a kappa of 3 to figure out what else changes. So capacitance would triple. Charge is the same, so the electric field from the plates is the same. This would be cut by a factor of 3. The relative, the electric field strengths stays the same. But if that stays the same, then this is a third, which means that the voltage is cut by a third. I felt like I shot off on my own tangent there. So, did you want to ask your question again, or was it answered?
So if you disconnect the battery, then directly it's affecting it's not affecting the voltage directly?
Not immediately. Because if I disconnected the battery now, go back to the problem, the first problem, then we stick a dielectric in, change nothing else, then I disconnect the battery. None of these numbers change if all I do is disconnect. Because, well, going through it, dielectric hasn't changed, so kappa is still the same. Area and D are still the same, so the capacitor is still the same. There's no reason for charge to come on or off. The charge is going to be fixed at that point. Charge is fixed. Voltage is the total electric field divided by D. D hasn't changed. Charge hasn't changed, so sigma is the same. Epsilon is the same. D is the same, so the voltage is the same. So nothing changes, just purely if I disconnect and do nothing else.
I think I'm probably asking what Daniel already asked, but, because I know in our master set, we disconnected the battery and inserted a dielectric. So our charge and our electric field, because of the plates, stayed the same.
Correct.
But there's not any, I might be asking what you're trying to ask, Daniel, like, are there any rules we need to know, or it's just, you just have to look at your numbers and make it make sense? Okay.
The latter there. I mean, just, again, it's the rule of battery still connected, voltage is going to stay the same no matter what else you do.
Okay,
You disconnect the battery, charge will stay the same no matter what else you do. And so it's the what else you do will start affecting everything else that's not fixed.
okay. So connected to battery, voltage stays the same no matter what, disconnect, charge stays the same no matter what,
Yes.
even with dielectrics and,
Right, because if I disconnect the battery, and again, I'm assuming an ideal disconnection, presumably it's in the videos also that in reality, it'll spark and you'll lose charge, but we assume a nice ideal disconnect. There's no place for the charge to go. So the charge has to stay fixed if you basically break the circuit.
okay.
adding a little bit more reality, let's say that I still have a nice clean break, somehow managed to break it fast enough so that no charge actually leaves it in a real situation. We live in the south, humidity. Eventually the charge would be leaving the plates. Gina?
The other day you said know how to add electric fields. Is that the same thing we just did in the first?
Yes, the
Okay.
very first thing we did,
Okay.
as well as what was done in the lab, as well as in a video,
Thank you.
at least one. All right, any other questions? Olivia?
Will stuff about area vectors be on this?
I mean, it's fair game.
Can we, if you don't have any plans after that, can we do an area vector problem?
Yep. My plans for this time is I will answer questions until there are no more questions concerning the first material, and then I will pick up on chapter 20. So a key thing about the area vector, it's perpendicular to the surface. This is supposed to be a three-dimensional scale here. Well, it's X, Y, and Z. And make that I hat, J hat, coming out of us, Z hat. So if I take a surface that is parallel to the YZ plane, sorry, that is the XZ plane. So if I take a surface that's parallel to the XZ plane, what is the direction, what is one of the directions of the area vector?
Up,
Or,
positive J hat,
okay, or,
negative J hat.
yeah, so it's either up or down. And where this matters is if you're dealing with electric flux. And if you recall, the electric flux, that is a capital Phi, is the electric field times the area. Anyone here in calculus?
Briefly.
Yeah.
Briefly calculus, have you gotten to integrals? Okay, so this one's for you. It's just a quick aside. Technically, it is the electric field dot dA. So that, all right, beyond the scope of the course, but just a little bit of this. And later on, for those who take calculus far enough, you'll see that and go, oh, that's what he was talking about. Okay. If you've had some calculus, this is just an antiderivative. All right, so anyway, E dot A. If the electric field is constant, then these are equal to each other. If the electric field is not constant over the area, then you have to do this. All right, before I keep going on with that, after this. So if I have an electric field, so it is a dot product here, and this is, the dot product is a scalar product, so my final answer is a scalar. Let's give some dimensions here. 4 meters by 6 meters. And I have an electric field that is, 5 newtons per coulomb I hat minus 3 newtons per coulomb J hat. So the first thing we need to do is figure out what is the area vector. So the magnitude of the area vector is the area. So what is the magnitude of the area vector?
44 meters squared.
And then the direction, you've already said. So the flux through that surface, and again, the flux is a measure of how much of this electric field is passing through a particular area. So this is just the dot product of these two things. So So we've got 5, I'm not gonna worry about units at the moment, minus 3J. Dot 24J. And when you're doing dot products, what are you multiplying?
The two J hats?
Yep. So we get negative 72 units.
Units time years per squared over.
You said it slightly off, but yes, I think you would have written it correctly. So Newton meter squared. For Coulomb, there is no nice one word for that. Yeah, they still find it bizarre, the things that they decide to name and things that they haven't gotten around to yet. So, if I put this, let's make it slightly more exciting. We'll keep the same surface there. This time I'll put my electric field in polar coordinates. Oh, I guess it's. Need something, so. Sorry? Yeah. Have you been waiting a while to come in? Okay. If you've not, I missed it, I'm sorry. So if the electric field is parallel to the XY plane and hits the area, the market area, at an angle of 30 degrees with respect to the vertical. Actually, which one's gonna make it more complicated?